So I'll start now, and today we'll start a new section, and that is on strut and tie models. Now, one of the additions to the Eurocode is this strut and tie models for structural design. So first we'll see what is meant by this strut and tie models. So basically, when you are designing members by using strut and tie model, it actually belongs to the plastic design philosophy. So basically what we do is we create a truss model, and then a truss model like this one. So we create a truss model to transfer the loads to supports when you have either concentrated or distributed loads. So these are the type of model that you get. You get the compression carried by concrete, tension carried by steel. So that's the type of model you get. And so basically compression is taken by concrete, and tension is carried by steel reinforcement. So this is actually based on one of the lower bound methods of plastic design. And according to this lower bound theorem, actually we use this lower bound theorem for all the structural design. What it says is the structural member does not fail if for the imposed load combination, a stress distribution can be identified for which the equilibrium is guaranteed. So you have to show that the vertical equilibrium, the loads are in equilibrium. So that's the first thing. And secondly, you have to make sure the stresses in materials are sufficiently low. So this is what we generally do in all our designs. So what we do is we perform an elastic analysis, and then we consider that this material behaves as an elastic material even during the service conditions. So basically, if we can ensure that we have the structural materials behaving in the elastic region, and also we have found a system of loads in equilibrium with the support reactions, then we can design that material using the normal theories. But once you perform the design, it does not mean that the structure is going to behave exactly as we have assumed. It could be that, certain places the material will go into plastic regions and so on as well. But what this theorem says is, if we are maintaining the stresses at sufficiently low levels, and also we are using ductile materials, then we don't have to worry about the actual stresses in the structure. There will be adequate redistribution of stresses if the stress is exceeded at one place, and it will result in a safe design. So that is the theory that we use in almost all the structural members. So that's why we like materials like steel, concrete, which can demonstrate certain amount of ductile behavior before the failure occurs. And then we make sure the stresses in the material also remains sufficiently low. And in the case of steel designs, generally we make sure the under normal service conditions, the stresses will remain even sometimes less than the yield stress. So if you have a structural member, we can actually divide it into two types of regions. One is called the B region, and that is the region where the basic assumption that the plane sections remain plane is valid. But there are certain places in a structure where you have discontinuity or concentrated loads are acting at a place. Then you will find this assumption that the plane sections remain plane is not valid, not strictly valid, very close to this discontinuity. Very close to the discontinuity, you will find that the assumption that the plane sections remain plane will not be valid. And those regions are called D regions. And so in a beam, you can actually identify D regions and B regions. And for example, if you have some discontinuity in a structure, say, you have a cantilever beam, small cantilever beam, and if that cantilever beam supports another beam with a stepped joint, so if I can actually give an example. So if you have a cantilever beam like this, supporting another beam like this, then we say, in this area, the plane sections do not remain plane because there are concentration of stressors acting at these places. So up to a depth d away, this depth is d, we say that, in this structure, the plane sections do not remain plane. Beyond that, it will come to the normalcy and you will get plane sections remaining plane beyond this point. So this is one example. Another example is, sometimes we get big beams supporting secondary beams. So at this place, we are getting a big load transferred. So you will find that in the main beam, in this region, the plane sections may not remain plane. So if this is the case, then you have to actually provide a lot of links around it to make sure whatever the load that is in this particular beam is now resisted by all these links, and transfer the load to the top of the beam, because generally we consider that the beams are loaded from above, not from the bottom. So if you are loading a beam from bottom, then you have to make sure additional links are provided to transfer the load that is acting at the bottom level to the top level. So this is also one situation like that, where we have a small beam supported by a main beam, and the small beam will transfer a concentrated load, and we have to make sure that concentrated load is transferred to the top part of the beam. So in such situations, we say, up to a distance of about d, the plane sections may not remain plane, and we might have to think about it. And the way that we respond to this situation is by providing additional links so that the loads can be transferred to the top of the beam safely. So you can have B regions, means Bernoulli, because he's the one who actually introduced the assumptions that the plane sections remain plane. So B stands for Bernoulli and correspond to the parts of the member where plane sections remain plane. And D stands for the discontinuity, where this assumption is not valid. So the places where this assumption is not valid is geometric discontinuity, like the connection between two beams, where one beam supports the other beam. And the static discontinuity is, the places where you apply highly concentrated loads onto the structure, and also at the supports, you will get this what you call D-region. So we'll look at one of the examples. So we look at the example of a deep beam, 6 meters of length, 6 meters of height, loaded with 3000 kilonewtons, transferred by a column over 1 meter width. So here this beam having a length of 6 meters, height of 6 meters, is supporting a column here. And the size of the column is 1 meter by the width of the wall. So if the width of the wall is say 0.25 meters, then the size of the column supported by the wall is 1 meter by 0.25 meters. So here you would see that all these are 0.5 meters. So the width of the support is 0.5 meters each. So here all these squares would be 0.5 meter by 0.5 meter, and over 0.5 meter we have a support condition. In this here also we have a support condition. So in addition to that, we are supporting a column here which will transfer a load of 3000 kilonewtons. So here we get 3000 kilonewtons, means this will transfer 1500, this will transfer 750, this will transfer 750. So altogether 3000 kilonewton load has been transferred onto the deep beam, and we like to see how this load would be transferred to the supports. We like to see how this load will be transferred onto the supports. So what we do is, now we can actually see how this behaves by looking at finite element model of this beam, and that will give us some indication how this is going to behave. So basically you will ask, how do you create a Fpm model of this type of situation? So first I will show you how you create the Fpm model, and then how you get this type of the directions for the main stressors. And here if you look at this situation, here we have a wall 6 meters by 6 meter, 6 meter height, 6 meter length, and at the center, over a length of 1 meter, we are applying a load of 3000 kilonewtons, and we like to see how these loads are distributed. So if you look at this one, you see this is a result of the Fpm model, and what you see is, the load that is applied here is gradually transferred in this direction, and the loads on this side is transferred here. And in addition to that, now you can see some blue color lines, and blue color lines actually respond to the tension. So at the bottom of the wall, you get tension, and all these loads are transferred to the support using the compressive strength of concrete. So in this region, the concrete acts in compression. This region also concrete acts in compression, and this region, you'll get tension, which means you have to provide reinforcement. And if you look at the way that the loads are transferred, you will see this is the way that actually the loads will be transferred. So before we go in deeper into it, we'll just have a look at how we create a Fpm model. So we'll create a model, because I can use the similar model for other structures as well. So what we do is we can start with a new model and we say grid only, because we are dealing with a beam of 6 meter and 6 meter. I will go for 12 grid lines in X direction, Y direction 2, and this direction also 12 grid lines. And I'll say the grid line spacing is 0.5 meters. And I can create the grid lines like that. And then what I do is I'll define a material, and here you can see this concrete. So I can make a copy of concrete. So I can say concrete 25, and I have to give the correct elastic modulus. So these cylinder strengths, so elastic modulus is about 27 e to the power 6, and the strength of concrete is 25,000, because we have to give all the parameters in kilonewton meter system. So these not newtons per millimeter squared, so it will be kilonewtons per meter squared. And then we can also define the area section. And if we add a new section, we say wall 225 or 250, and you can see it's defined as 0.25, but here we change the concrete strength to 25 megapascal. So you have 25 megapascal concrete and wall thickness of 250 millimeters, and you can say okay. And now we have to create the shell elements to represent the wall. So what we can do is we can go and see the view at y is equal to 0. So this is how the deep beam looks like. And so if you want to create the beam, deep beam, which is having a length of then should be 6 meters. I have got only 5.5 meters. So what I can do is I can go there and can say spacing rather than coordinates. And if I go to the end, so this looks like, it's ending at starting at 0. If you look at the ordinates, so you can see the last one is 5.5 meters. So that's the problem that we encountered. So what I have to do is say copy paste N and N KLMN M, and I have to now it's 6 meters, and here also I might have to add one more because the height has to be 6 meters. So I have to go for Z13. And so coordinates looks okay. Coordinates 0. How it looks like. Okay. Okay. So now you can see we have 6 meters here. The height is also 6 meters. Now we can view 2D. So now I can draw all the shell elements in one operation. So you can see once you have the grid, you can just draw all the shell elements in one go. So it's wall. And then if you are going to have a concentrated load of 3000 kilonewtons applied over a length of 1 meter. So this is 2.5 meters. So you can see that there are 3 nodes because this load is acting over 1 meter, and we can say these 2 nodes will carry 750. I have only the dead load case, so what I do is I will define another load case. We call it live, and so what we do is we will assign joint loads at these 2 locations of magnitude minus 750. So the total load is 3000. So we'll in the center one we'll assign minus 500, 1500. So there are 3 loads applied, 750, 750, 1500, altogether 3000. And here we'll also define some support conditions. So generally when you are designing the supports, it's a good practice to restrain only one point, and the support will be there over a length of 0.5 meters. So instead of, so I will go for 2 concentrated supports. So the distance between these 2 is 0.5 meters. And then I will assign joint restraint only in Z direction. So I'm supporting it, but no other variation. So it's supporting, and it can expand this way because I have put all these on roll supports. So then now the loads have been applied, the support conditions have been defined. So I can save this as, we say, dbeam3. You can save it at a place that is convenient to you. And then I can say run analysis. So get the deformed shape of the hole due to this reasonably heavy load that is applied at the top, which has a magnitude of 300 tons or 3000 kilonewtons. So we are getting a deformed shape like this. And we can now look at under the live load. So now you have this principal stresses evaluated. So we are going to have a look at this. And here you can see that, all these loads, although we apply the load here, automatically the load will be moving towards a path like this. And the reason is that, these supports will act like rigid. So because of that reason, due to the flexibility of the wall, you will find that, the wall will utilize the compression carrying capacity of concrete and shed the loads onto the 2 supports. But because these are at an angle, so there is a compression. So this is the compression path. So when you have one compression this way, another compression this way, then if you take the horizontal component of all these forces, then you can find the reinforcement needed in this area. The reason is, if you look at all these ones, you can see the forces. The minimum is 666, and here you can see the forces. The maximum value is 760. So basically, this is a tension region at the bottom. On the sides, you will get the region where the strut can transfer the load onto the supports. And because there are inclined forces of compression nature, we have to provide tension reinforcement at the bottom. So here we say, we are actually looking at a strut and tie method. So these are the struts, and this becomes the tie. The strut and tie method, where these will become the compression struts or columns, and this part will become a tie. So we have to provide reinforcement here, and also we have to check this reinforcement in these areas to make sure that the loads on the walls will remain at reasonable levels, or stressors will remain at reasonable levels. And in addition to that, most of the load from above will be transferred onto the supports so that you can maintain the equilibrium. So these one of the examples. So basically now you have seen the way that the FEM can be used to predict the way that the loads are transferred, and so you can see that the loads will be transferred this way, and there will be a tie this way. And this diagram also indicates the tensile stress, compressive stress trajectories, this one, and also tensile stress trajectories in this way. So basically our equivalent model will be something like this, where the load here has a magnitude of P, and part of that force will be, or half of that force will be transferred along this strut. The remaining half will be be transferred on this side, that is the right hand side. And then if you apply a force P, the reaction will be P by 2 in each pile. So you can actually design a wall supported by piles, considering that the wall will behave like a deep beam. So now let's look at this arrangement. And if you look at this arrangement, let's say the thickness of the wall is something like 250 millimeters or 300 millimeters. Then what happens is, here we are applying a concentrated load onto the beam, and it has a bearing area of A1. And what actually happens is, this load has to be transferred onto the two columns, and it will be transferred at an angle, and this angle will depend on the height of the it will all depend on the height of the wall that supports the concentrated load. So here you can see, when you apply a load this way, then this is in compression. That means, you know, we have a load acting this way, and using the strength of concrete, we are transferring the load to these two places. And if you look at this angle theta, it actually depends on this angle theta, and angle theta depends on the depth up to this level, that is centroid of this reinforcement, and it also depends on the distance between the two piles. So the first thing that we can see is, if you apply a load P, what is the force in this compression strut? Or what is the force in the strut? So that is the first question you can ask. So what you can say is, if the load is P, P by 2 will be carried by the left hand side, remaining P by 2 will be carried by the right hand side. So basically you can see the load transferred onto each strut is P by 2. So the force in the strut should be in equilibrium with the load of P by 2. So because of that reason, you can say the load to be resisted by the strut is given by the portion of the load transferred divided by sine theta, So basically, if you want to transfer a load of 1000, then in the inclined member, you have to have a load of something like 1200 or 1300, so that when you take the vertical component of the inclined strut, it will be in equilibrium with the force that is acting vertically downwards. So this force P, we can convert it to P by 2 considering only one side. So this load P by 2 should be in equilibrium with whatever the force in this strut, but you have to take only the vertical component of it. So basically what you are saying, if the force in this strut is PC, PC sine theta is equal to P by 2. PC sine theta is equal to P by 2. So that's what we actually need to provide. So basically what you have to keep in mind is always the force in the strut will be higher than the load that you want to transmit. Because we have to say that, you know, this load is in equilibrium with the forces in the strut. So that's the first equation. And if you want to know how much load will be taken by the tie, then you have to see what is the horizontal component of this inclined force. What is the horizontal component of this inclined force? So inclined force is PC. So the horizontal force will be PC cos theta. PC cos theta. But here we can see, you know, PC is equal to P by 2 sine theta. So in that case, we can say the load in the ties will be equal to P by 2 divided by tan theta. P by 2 divided by tan theta. Or here you can simply say P by 2 tan theta. P by 2 tan theta. So basically, it's a straightforward task to identify the tensile force that will act in the tie. And once you know the force, you can always provide the reinforcement to carry that force. So that way we can actually work out the reinforcement needed. So the tensile force PT can be resisted by a bundle of parallel bars. It is essential that the bars are effectively anchored in the nodes. So basically what it says is, when you have this reinforcement, it has to be properly anchored either as a straight bar. If the length of the straight bar is too much, we can bend this bar upwards. But then you have to consider that, you know, it is a strut where the anchorage has been provided in both the horizontally and vertical. So basically the tensile force is PT and it has to be resisted by the bottom reinforcement. And the other important thing is, you know, this reinforcement should not be concentrated. we can distribute the reinforcement. So the reinforcement required can be provided in multiple layers. And also if the depth of the beam is about 0.6 meters, then you can actually spread the reinforcement in the bottom 10% height of the wall. So generally, when you consider the bottom 10%, because the wall height is 6 meters, you get 600 millimeters. So you can see this bottom reinforcement can be spread over a height of about 0.6 meters. 0.6 meters. So, and to find the reinforcement, you divide the area, the load by the stress, then you get the area. So that way you can find the reinforcement required at the bottom. But we, in addition to that, we have to also look at the struts. You have to look at the struts, and so for struts, we can see the way that the loads are transferred. Here you can see the loads are transferred. This is the load from above, and it will be resisted by these two struts. That means the struts will be will be carrying a load. And here also you will find another kind of equilibrium, and that is, the reaction is in equilibrium with the load transferred through the strut. And in addition to that, because these loads are now in this direction, to prevent the failure of this joint, you have to provide tension reinforcement this way. So here you get tension, here you get compression, here you get compression. So you get a situation which is different to this place. At this place, you get compression this way, compression this way, compression this way. Whereas here, you can see there's one compression, another compression this way, and the other one is tie force. So you can have different types of joints when you are using strut and tie models. And if you look at the compression struts, it is necessary to find the axis of the concrete compression struts in a truss model, and also reasonable values for the dimensions of the cross section of the strut. So basically, one of the options is we consider that the strut is going to be like this. But in actual practice, what happens is we are applying a concentrated load here, then it will start distributing like this, having a greater width, but finally it will converge to be in equilibrium with the forces transferred through the support. So first we look at what's going on at this place, and if you look at this dimension as A1 and the thickness of the wall as B, then the vertical stress at this place will be P divided by A1 B, P divided by A1 B. So you can say so if we consider that the width of the strut is A3, width of the strut is A3, then the cross section of the strut will be B times A3, B times A3, and if you look at this diagram, you can see this angle is theta here. This angle is theta, And this full one is A1. So this length is A1 divided by 2. And this horizontal angle is theta. So this is 90 minus theta. And this is theta. So this is 90 minus theta. So here you get an angle of theta. So this angle is theta. So here also theta. Then this 90 minus theta, and also here you get angle theta. So if you want to find this distance, then you can say this distance is equal to A1 divided by sine theta. A1 divided by sine theta. So not A1 divided by 2 divided by sine theta. So B times A3 is equal to B multiplied by A1 divided by 2 divided by sine theta. So if the force is P3 here, then the value of P3 is equal to P over 2 sine theta. The value of P3 is equal to P over 2 sine theta. So you can say the stress in the strut is equal to the force in the compression strut divided by the area, and the force is equal to here P over 2 sine theta, and B times A3 is given by this expression. Then you will find that the stress in the strut is given by P over B times A1, and here you can see the stress in the strut is also equal to the stress under the contact location. The load is P. The stress here is P divided by A1B. The stress here is P divided by A1 times B. And if you look at the stress in the strut, that is also P divided by B times A1. So which means here you get a stress and an equal stress this way and an equal stress this way. So in this particular strut location, you will see that all the forces are compressive and the compressive stresses are also equal. So, and we say that if the stresses are equal in all directions, then we say that it's like a place where you get hydrostatic pressure. When you have hydrostatic pressure, the pressure is equal in all directions. So in a joint like this, you'll get that pressure is, or the stress is equal in all directions. So this indicates that the stress in compression strut is equal to the stress in the contact area between deep beam and the column that introduce the load onto the deep beam. Hence, it can be stated that this node is subjected to the same compressive stress in all directions. So this is one of the joints that you get where the concrete is in compression in all directions. So the compression, so if you look at the situation here, the compression stress in the struts are resisted by concrete, and it should be taken as a fraction of FCB. So here you can see this is in compression. The value that can be used for this fraction will depend on few other factors as given in this particular clause. So we'll see what are those different situations. So if you look at this particular location, we have shown that it's under stress, compressive stress in all directions. So which means, you know, it's a fairly favorable situation. Whereas if you look at this particular joint, here you can see you get compression. This way also you get compression, whereas you get tension in the steel. So this can lead to certain amount of cracking in concrete, because we have something, one force in tension. So because of that reason, the force carrying capacity of this type of place will be lower. This type of place will be lower. So the most important thing is, you know, we have to see that whatever the force that is transferred here can be transferred to this location without any failure of the concrete here. Without any failure of the concrete here. So in the strut and tie, once you know the force, you can easily find the reinforcement needed. But in addition to that, you have to check the stress in the strut as well. Stress in the strut as well. So one of the things we have shown is at this place, it's in compression this way, compression this way, compression this way. It's a fairly favorable situation. Whereas here you get compression, compression and tension, which is less favorable. So we can allow this different values of for the concrete strength in transferring these forces. So in compression nodes, where no ties are anchored, so these call a compression node. So we call it CCC node. So these compression, 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 this is called CCC node, whereas we call this CCT node. So here you get compression, compression and tension. And there's a possibility that you might get a joint where you have compression and tension as well. So depending on all those situations, we can have different joint conditions and different values for the maximum stress that we can allow in a strut. So in compression nodes where no ties are anchored, so you can see the maximum force carrying capacity is given by this equation, which is given in Eurocode, and it says it's K1 times nu FCD. The value recommended for K1 is 1, and value of nu is 1 minus FCK over 250, and FCK is about 25 or 30. So you can see this value is about 0.9, and FCK is the strength of concrete, which is taken as the compressive strength of concrete. So what you get is compressive strength of concrete divided by 1.5. Compressive strength of concrete divided by 1.5 multiplied by 0.9. So what you get is something like, if you get 0.9 divided by 1.5, so you get 0.6 FCK. So you can see the force that can be carried by concrete will be equal to 0.6 times the strength of concrete if you are using 25 megapascal concrete. 25 megapascal concrete. If you are using 30 megapascal concrete, it can be slightly less. So you can see 60% of the strength of concrete can be used for carrying compression. Whereas if you look at this situation, where we have compression in one direction, compression in the other direction, but tension in the other direction, like the bottom joint of this particular diagram. Here, this is the situation that you get at this location. And here you can see the strength is given by same equation, but this time the value of K is 0.85. Value of K is 0.85. Value of K is 0.85. But if you have a situation where you have compression but tension in two different directions, compression and tension in two different directions, then it's given by 0.75 times the strength. 0.75 times the strength. So this is the strength of concrete. This is a strength reduction factor, and 1.5 is the factor of safety. So it's given by 0.75. 0.75 multiplied by 0.9 divided by 1.5 gives a value of 0.45. 0.45 FCK is the strength with 25 megapascal concrete at a joint like this. Whereas if the joint is like this, then we have to use a factor of 0.85. 0.85 into 0.9 divided by 1.5 gives 0.51. 0.51. So for different locations, you have to use different strengths. So in the strut and tie models, we have to actually check the stresses in strut and also stresses in strut and also the amount of steel required in the tie. So once you check both, if the stresses in the strut are low enough, you have provided sufficient reinforcement, and that reinforcement is properly anchored here, then you will find that within a D region, like a deep beam, the loads can be transferred onto the supports without considering the flexural action, but by considering the behavior as a strut and tie model. Strut and tie model. So this is the theory behind strut and tie.